So a matrix is a rectangular array of numbers with m rows and n columns. So when we say Rm by n, this simply means that it's the collection or set of all m by n matrices whose entries are real numbers. Now matrices will usually be denoted by capital letters. So uppercase A is a matrix, and to explicitly define its entries, we're going to use the bracket notation, that is Aij. So subscript ij will index the rows and columns, I for the rows and j for the columns. Now a vector, on the other hand, is a matrix, is a special type of matrix. So it's with either one row or one column. So for example, if I go ahead and say x is 1, 2, and 6, then x is a column vector, right? It is a matrix of size 3 by 1, right? So it falls in the collection R3 by 1. So it belongs to that collection. When we say a vector y is, let's say, 6, 1, minus 5, this is a row vector. So this guy falls in R1 by 3. So unlike the matrices, where we need two indices to extract its elements, vectors require only one index. So when I go ahead and say here x3 is 6, right? And here let's say y1 is also 6. So an example on this indexing is the following. Let's say I have a matrix A with entries aij, where aij is 1 over I plus j. Now, if we say, oh, I need a matrix of size 3 by 4, so A falls in R3 by 4, then it should be understood that I takes values from 1 to 3 and J takes values from 1 to 4, right? So if I want to fill in my matrix A, it should look something like this. A11 down to A34, right? So using this formula, we can fill in the matrix. So A11 would be 1 over 1 plus 1, which is 1 over 2. A12 would be 1 over 1 plus 2, which is 1 over 3. A13 would be 1 over 1 plus 3, which is 1 over 4, and so on, right? So if you want to extract any columns of A, say the second column, it is just this guy, right? So you can also extract columns from A. This will turn out useful in future lectures. So this is how we define matrices. All you need to know is that a matrix is an array of numbers with m rows and n columns. Now let's talk about the equality of matrices. When do we say that two matrices, A with entries aij and B with entries bij, are equal? They're equal if they have the same size, first of all. So first, you can't compare matrices which are incompatible. So if A falls in Rm by n, then to compare A with B, B should also fall in Rm by n. Okay? This is one thing. And the second thing is that their corresponding elements should be equal. That is, Aij should be equal to Bij for all I going from 1 till n, and j going from 1 till n. Right? So an example is the following. Those two matrices first are of the same size, and comparing its entries, 1 is equal to 1, 2 is equal to 2, and so on, we can say that both matrices are equal. However, those two are not equal even though their entries are the same. A11 is B11, A12 is B12, A21 is B21, and A22 is B22. However, they're not of the same size. A belongs to R2 by 3, whereas B belongs to R2 by 2. So those two are not equal. Now let's talk about adding matrices. So say I've got two matrices with entries Aij and the other one B with entries Bij. So to add two matrices, also both should be of same size. Both of them fall in Rm by n, let's say. That is, they have the same number of columns and the same number of rows. And A plus B, the matrix A plus B, is formed by just adding element-wise the entries of A with the entries of B. That is Aij plus Bij. So as an example, we've got those two matrices A and B, and we're interested in adding them. A plus B is obtained by simply adding 1 by 2, 2 by 1, 3 by 7, and so on. So 1 plus 2 is 3, 2 plus 1 is also 3, 3 plus 7 is 10, 0 plus 6 is 6, 1 plus 0 is 1, and 0 plus 6 is again 6. Let's talk about scaling matrices. So say I've got a matrix A, elements aij, and a number t, that is an R. Then Ta, the matrix Ta, is simply a matrix obtained by multiplying the elements of A by T, that is T times Aij. A small example on that would be, say I've got this A, which is 1759, and T is 2. Then all I have to do is multiply the entries of A by 2. So 2 by 1 is 2, 2 by 7 is 14, 2 by 5 is 10, and 2 by 9 is 18, right? Let's talk about the negative of a matrix. Say I've got a matrix A, that is, then minus A is again a matrix of the same size obtained by just negating the elements of A, that is, minus Aij, as such. An example would be the following. Say I have this matrix A, then minus A is obtained by just flipping the sign of its entries. That is, minus 1 becomes a 1, 2 becomes a minus 2, 3 becomes a minus 3, and minus 4 becomes a 4. So since we define the negative of a matrix, we can now subtract matrices. So given two matrices A and B, then A minus B is defined as A plus minus B. So we're adding two matrices, A and the negation of B. That is Aij plus minus Bij. That is simply Aij minus Bij. So we're just subtracting the elements of A and B. An example on that would be, say I've got A and B as such, then A minus B is obtained by subtracting the elements of A and B. So minus 1 minus 2 is minus 3. 2 minus minus 1 is 3, 5 minus 3 is 2, and 7 minus minus 7 is 14, right? Let's talk about the zero matrix. So in any field, we can define the zero element. So when we talk about matrices, each n by n matrix, all of whose elements are 0, is called the zero matrix. Of course, of size m by n, and is denoted by the symbol 0 as such. It's not the 0 that you use in the real numbers, no. It's a zero matrix. So it's a matrix if it falls in m by n, then it's a matrix of m rows and n columns where all its elements are zeros, right? That said, now we can talk about some laws of arithmetic. So given three matrices of same size, A, B, and C, all of size m by n, and two scalars, s and t, so s is an r and t is an r, then the following is true. A plus b first plus c is equal to a plus b plus c. So the order of addition does not matter. 2, a plus b is the same as saying b plus a. Commutativity of the addition. 3, 0 matrix plus a is again a. We know that. 4, a minus a is 0. We also know that. All those are trivial. They share the same properties as real numbers. Now if you grab two scalars, add them up, then multiply them with a matrix A, it's the same as saying s times a plus t times a. You're distributing s by a plus t by a. 6, you can say the same thing about subtraction. S minus t times a is s by a minus t by a. 7, you can do the same thing but in terms of matrices. So let's say you've got t times a plus b, and it's ta plus tb. You say the same thing with subtraction. A minus b is ta minus tb. 9, s times ta is the same as st by a is the same as t by sa. Okay, so it doesn't matter which scalar you multiply first with the matrix. 10, ta is 0 implies that, zero matrix of course, implies that either t is the usual 0, the 0 real number, or a is the 0 matrix. Now let's talk about matrix product. Say I've got two matrices, A and B, but this time of sizes, A is of size m by p, and B is of size p by n, such that the number of columns of A equals the number of rows of B. Then AB, which we will denote here by matrix C, indexed by element Cij, is of size m by n. Right? Now, how do you obtain Cij? It's not element-wise multiplication, no. It is obtained by the following formula. So you sum up aik times bkj over k from 1 till p. That is ai1 times b1j plus ai2 times b2j all the way down to aip times bpj. Now a nice way to visualize this is to lay down both matrices A and B. So I just laid down the matrices A and B that is equal to C, and we want to compute Cij. So how do we do that? We want to visualize what's going on. Well, since we want to compute Cij, I stands for the ith row in A. The ith row is this guy over here. So it is AI1, AI2, down to AIP. Now, I put it as a column. It's not a column, it's a row, but we just want to lay them down as such. Bear with me just a second. And J stands for the jth column in B. That is this guy over here. Notice that the blue and the green columns are same size. So, how do we compute Cij? It is obtained by a simple inner product between the two vectors. That is, we multiply corresponding elements together, that is AI1 with B1j, AI2 with B2j, down to AIP with BPJ, and then we add the results to form Cij. So Cij is obtained simply by multiplying AI1 with B1j, AI2 with B2j, down till AIP with BPJ, then adding them all up. Okay? Let's do a simple example. So 1, 2, 3, 4 multiplied by 5, 6, 7, 8. First of all, could we multiply these two matrices? Yes, because the number of columns of the first one is equal to the number of rows of the second matrix. How do we do that? So the output is of size 2 by 2. Now to obtain the first entry, this guy over here, we grab the first row of A and the first column of B. Multiply, then add. So 1 by 5 is 5 plus 2 by 7 is 14. So 5 plus 14 is 19. Next, to compute C12, so the guy over here, we grab the same row of A, but this time the second column of B. So 1 by 6 is 6, 2 by 8 is 16. Add them up, you get 22. Now, to compute C21, so this guy over here, 2, 1, we grab the second row of A and the first column of B. So 3 by 5 is 15, 4 by 7, 28. 28 plus 15 is 43. Now to compute C22, the guy over here, we need the second row of A and the second column of B. That is 3 times 6, that's 18. 4 by 8, that's 32. 18 plus 32 is, so that's how you get the job done. Now, a remark here for those of you interested in computational linear algebra, this is a good remark. So matrix multiplication is a computationally expensive operation. On a computer, multiplication is a much more time-consuming operation than addition. When you come and think about it, computers perform multiplication by multiple additions. So of course, multiplication is more expensive or time-consuming than addition. Now, let's say you have a matrix A of size m by k and another matrix B of size k by n. Well, if you want to compute one entry of AB, the multiplication, the matrix AB, well, let's focus on one of its entry, ij. Well, ij, as we saw over here, requires k products, right? So here we've got 1, 2, down to p. So p products, in this case, it's k products. And this must be done n times to form each row of AB. So computing one entry of ij requires k products or multiplications. So if you come and think about it, To compute one row of AB, that's denoted by, I don't know, I as such, so one index, this is the ith row. So to compute only one row, we would require, how many elements do we have in the row of AB? We have n elements, so n elements in a row. So this means we require, to compute only one row, k times n multiplications. So k n times. So kn multiplications. Now to compute all AB, how many rows do we have? We've got m rows. So in total, you need m kn times. So m kn multiplications. That's a lot. In practice, this is a lot. So a particular case here would be if we're focusing on square matrices. So if A is n by n, so for square matrices, we've got m equal k equal n. So the total number of multiplications becomes nq, right? nq. So that means if you have two matrices of size 10 by 10, then you need 1,000 multiplications. If you have two matrices 100 by 100, you need 1,000,000 multiplications. That's very, very expensive. Now, we're being too extreme here. In some applications, matrices are not dense. That is, the opposite of dense is sparse. What does sparse mean? It means that most of the elements are zeros. It means less multiplications. So even though you have large matrices, sometimes it happens that you can cut down this expensive number of multiplications. You can multiply less. There's many fast ways that handles or multiplies sparse matrices. We'll be talking about this in future lectures. So that's a practical remark. Keep it in mind. So how many operations do I need to multiply two matrices? It's mkn. Let's talk about some properties of matrix products. So first thing, keep in mind that matrix multiplication obeys many of the familiar laws of arithmetic apart from the commutative law. That is, AB is in general not equal to BA. Now for those that commute, for matrices that commute, they belong to a special class. We'll talk about this in future lectures. But in general, this is not true. So AB is not necessarily BA. 2AB first times C is A times BC. So the order does not matter. 3, if we've got a scalar T multiplied by AB, it's the same as saying, oh, it's TA multiplied by B, or it's the same as saying A multiplied by TB. That being said, if you've got a scalar hanging outside the product, you can just absorb it inside any of the matrices you wish. 4, say I've got a matrix A plus B times C, you can distribute AC plus BC, right? And 5, if you've got a D multiplied by A plus B, you can also distribute that. So whether on the left or on the right, you can still distribute over addition. Okay, now that we defined what matrix product is, we can go ahead and, show a really nice example. So let's say you've got the following system of equations. X plus y plus z is 1, x minus y plus z is 0, 3x plus 5y minus z is 2. You can go ahead and solve this system the hard way, that is, by elimination or substitution or whatsoever, or you can form matrices now. You can write this as follows. So 1, 1, 1, 1, minus 1, 1, 3, 5, minus 1 times a vector of unknowns x, y, z is equal to the right-hand side, 1, 0, and 2, right? So this matrix, call it A, and this vector, call it B, are given. They're the coefficients of the system. A could be extracted from the coefficients of x, y, and z, the three equations. So the first row are the coefficients of x, y, z respectively. Same for the second and third rows, right? Likewise, B contains the corresponding coefficients on the right-hand side of each equation in the system. XYZ is a vector of unknowns. Let's call it, I don't know. We're out of notation here. Call it vector C. So AC is equal to B. Given A, given B, find C. In future lectures, we're going to talk about matrix inversion. So You can simply solve this by inverting A, then multiplying it with B. You can also recognize that this system could be represented as x multiplied by the first column of A, 1, 1, 3, plus y multiplied by the second column of A, 1, minus 1, 5, plus z multiplied by the last column of A, which is 1, 1, minus 1, right? This is all equal to the right-hand side, which is 1, 0, 2. You can go ahead and solve this for the moment using any method that you like. You'll find out that x is 0, y is z is half. But the point of this example is just to show you that you can translate system of equations into matrix products. Okay? Now let's define one very important operator that deals with matrices. That is, it takes a matrix in and throws or outputs a number. The trace is a matrix operation that is frequently used in matrix formulas, and it is very simple to compute. So how do we define a trace? Given a matrix A that is square, so no n by n matrices here, it's a matrix of n by n. So trace is not defined for rectangular matrices, only for square matrices. Keep this in mind. So if someone comes and tells you compute the trace of, I don't know, 1, 2, 3, 4, 5, 6, you should tell them, well, it's not defined. There's no answer for that. The operator does not accept rectangular matrices as input, okay? So this guy is not defined. Okay, so the trace written as trace of A, or for short TR of A, is the sum of the diagonal elements of A. That is A11 plus A22 down to ANN. Okay, so as an example, say I've got the following matrix. The trace of A is just the sum of diagonal elements of A. So 5, 4, minus 6, and 3. Right? 5 plus 4 minus 6 plus 3, which is 6. Okay? There's a lot of properties of the trace, one of which is that trace A plus B is trace A plus trace B. However, trace AB is not trace A times trace B. This is not true. Of course, this thing works for subtraction as well, so if I have a minus, you could subtract the traces. Also, if you have trace scalar T times matrix A, it is equal to T times trace of A. Okay? One very important property of the trace when you're talking about product of matrices, so trace AB, it is true that it is not trace A times trace B, but it is equal to trace BA. So you can commute multiplication when talking about the trace. Okay? This is also called the cyclic property of the trace. Grab B, you throw it behind A. Okay? So that's it for this lecture. I hope you enjoyed it. We talked about a lot of stuff here. We started off defining what a matrix is, the collection of all n by n matrices, what row and column vectors are. We talked about equality of matrices, so when do we say that two matrices are or are not equal? The addition of matrices, how to add two matrices, how to scale matrices by a scalar, how to compute the negative of a matrix, how to subtract matrices. We defined the so-called zero matrix, and we gave some usual laws of arithmetic on matrices, of course. Then we talked about a very important topic, which is the matrix product, how to multiply two matrices, right? Then we gave a remark on matrix multiplication, that is, if you want to compute matrix multiplication on a computer, how much time does it consume? That is, what is the time complexity of a matrix multiplication? Some properties were given on matrix multiplication as well. A small interesting example was given on how to translate a system of equations into matrix multiplication. Last but not least, we introduced a very well-known operator done on square matrices, that is the trace operator, how to compute a trace of a matrix, and some of its well-known properties. Thanks for watching. If you found this lecture beneficial, please consider subscribing to the channel and liking the video. If you have any questions whatsoever, please leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Thank you so much, and I'll see you in future